Thanks a lot for inviting me. So this is a joint work with Edith, Xin, Jelani, Tamás from Google Research, and also my student Moshe from Tel Aviv University. And this talk is about the robustness of a classical algorithm, a classical streaming algorithm called CountSketch to adaptive or adversarial settings. So before I speak about CountSketch specifically, let's recall the differences between the classical or oblivious streaming setting and the adaptive streaming setting. Okay, so in the classical oblivious streaming setting, we have a streaming algorithm. And we assume that there is some fixed but unknown stream of inputs. We don't know this stream in advance, of course, but we assume that it is fixed. Now, on every time step, we get the next input update from the stream, process it, and we need to come up with our current estimation for the value of the function that we are trying to estimate. Then we get the next input, output our next estimation, and so on. Okay, so that's fine. What happens on the other side of the screen? So we still have our streaming algorithm. But now, the stream is not fixed in advance. Instead, we assume that there is some adversary that chooses the updates in the stream adaptively as time goes by. So first, the adversary chooses the first input update in the stream. We get it, process it, and come up with our first response. Now the adversary gets to see this first response, and based on that, chooses the next input in the stream. We get it, give out our next output, the adversary gets it, based on that, chooses the next input, and so on. Now, the issue with the adaptive or adversarial setting is that if you think about it, so the adversary chooses the second input based on our first output. And if the streaming algorithm is randomized, then that first output depends on our internal randomness. And as a result, the second input and the third input and so on, they all depend, at least somewhat potentially, on our internal randomness. So we are in a setting where the inputs that we get depend on our internal randomness. And that's a problem. It breaks a lot of the analysis of classical streaming algorithms. So that's the issue. We want to design streaming algorithms that provably maintain accuracy even in such an adaptive or adversarial situation. So if you've seen talks about adaptive streaming over the last 2 years, then this is typically how they present the setting. Before we proceed, I want to make a slight modification to the model. It's just for convenience. Instead of assuming that the adversary on every iteration specifies just one update in the stream, I want to assume that it specifies like a burst of updates. It doesn't change much really. It just allows me to bound the total number of outputs that I give out. Or alternatively, I call them queries. So in every iteration, the adversary specifies like a burst of updates, we get them one by one, and then we give out our current estimation for the value of the function so far. Then the adversary specifies another burst of inputs, we get them one by one, give out our second estimation, and so on. So in total, I have like big T time steps at which I am querying, at which I need to give out an output. Okay, so that's the setting. More formally, so basically here is the definition that says that the previous picture is the definition. First, we agree on some function that we want to estimate. This function takes a prefix of the stream, so every update in the stream is an item between 1 and n. So the function takes a prefix of the stream and gives out something out of a range R. Now we think of a two-player game between a randomized streaming algorithm and the adversary, where for T rounds, the adversary chooses a burst of input updates, the streaming algorithm gets them one by one, and then outputs its current response ZI. And the goal of the adversary is to force the streaming algorithm to have large error or to have large space. And one thing I want to mention is that an important special case that people have been thinking a lot about is when the range of the function is the real numbers, and in which case we typically aim for estimating the value of the function up to a small multiplicative constant. Okay, and another thing I want to mention.
Okay, yeah.
Another thing I want to.
Sorry,
yes.
So here do you allow the deletions or is only insertions?
Great question. This talk is focused on the insertion deletions model, so we allow deletions.
Okay, you allow deletions. Okay.
I allow deletions. So in particular, if you think about it, here, because we allow deletions, from one burst to another, the adversary could like completely undo whatever it did before. Yes.
Yes.
If it wants. Okay. So and another thing I'll mention is that in classical streaming without the adversary, we typically aim for streaming algorithms with polylogarithmic space in like the number of queries and let's say the total number of updates throughout, which let's denote by n. Okay. Great. So we understand the picture or the model of adaptive streaming. What can we say about it? So first, it's very easy to show that if you have a deterministic streaming algorithm that works in the classical setting, then this algorithm works as is also in the adaptive setting. Intuitively, we kind of said that the problem is that the adversary might generate dependencies between the inputs and the internal randomness. So intuitively, if there is no internal randomness, then you're fine. Also, some randomized streaming algorithms, they just work as is or with very minor tweaks, even when you talk about the adaptive setting. But not all of the randomized streaming algorithms. For example, for estimating the frequency moment, the second moment of the stream, we know that your algorithm must probably be randomized, and there are known attacks showing that classical streaming algorithms for that problem don't work very well in the adaptive setting. Okay, so what about negative results? So if you talk about the setting where the range R of the value of the function that you're trying to estimate is arbitrary, then you could easily come up with examples where the streaming algorithm in the adaptive setting, its space must grow linearly with the number of queries that you aim for. And if you think about it, that's like the worst situation you could be in. Because trivially, you could always take a classical streaming algorithm, duplicate it t times, and then use every copy just once in order to answer a single query. So a linear blow-up is like the worst thing you can have. For the case where the range is just the real numbers and we aim for a multiplicative error, then we have we know of a specific weird problem for which there is probably a blow-up of root t in the necessary space in the adaptive setting versus the classical setting. Okay, so these are the negative results that we know about. What about generic constructions? Okay, so like I mentioned, it's trivial to get linear blow-up in space in the number of queries t. And so, since it's trivial, let's just agree that if you have a streaming algorithm that is robust or maintains accuracy for at most a linear number of queries in the size of the sketch, then this sketch, let's just call it a non-robust sketch because it's trivial. And a generic result that I'll survey in the next slides says that there is some kind of a generic wrapper using techniques from the literature of differential privacy that allows you to transform a classical non-robust streaming algorithm into a robust one. And the price or the blow up in space that you will pay when you use this transformation, that will depend on the specific problem that you're trying to solve or on the range of the function that you're trying to estimate. And in particular, in case that the range is just the real numbers, then the blow up is at most root. Okay. And one more thing I'd like to mention is that if you are interested in insertion-only strings without deletions, then there are a lot of other things you could do, but this is not the focus of this talk, so I'm not going to talk about it.
So,
questions?
Since you talk about this difference from insertion-only streams, so for the negative results, are they already for the insertion-only? Or can you say that for if you allow deletions, can it be even harder, potentially?
Okay, so these negative results are for deletions.
For
you allow deletions.
Yes. Sorry. Without deletions.
With deletions. The negative results are with deletions. Yes.
Okay, so then does that mean if you only are insertions, then do we have similar negative results, or is actually unknown?
So for the case where the range is the real numbers and you aim for multiplicative error, then in insertion-only streams, you typically get something which is very close to the classical setting.
I see. Thanks.
Intuitively, the reason is that in insertion-only streams, the value of the function only grows. And since you aim for a multiplicative error, then you don't need to update your estimation many times.
Yeah, sort of you can do a certain type of bucketing. Yeah.
Yes.
Yeah.
Okay, so this is what I want to survey next, because our result is based on this previous generic construction. So to do that, I first need to recall what is differential privacy. So differential privacy is a mathematical definition for privacy that aims to enable statistical analysis of databases while ensuring that the outcome of the computation leaks almost no information about every single point in your database. So mathematically, differential privacy is kind of a stability requirement from an algorithm that takes a database as an input and outputs something. And specifically, the requirement is that for any two databases that differ on only one point, we call these neighboring databases, then the outcome distribution of your algorithm when you run it on the first or on the second neighboring database should be very close. Specifically, this is typically quantified using multiplicative parameter epsilon and an additive parameter delta, but this is less important for my talk. You don't need to remember these epsilon and delta. For my talk, and also in this talk, I don't care about privacy, about differential privacy as a privacy concept. I only care about it as a stability notion, as a mathematical concept. So here is an interpretation or the reason of why we think about this definition of differential privacy as a mathematical concept. But like I said, it's less important for this. Basically, the only takeaway I need from this slide is that differential privacy, if your algorithm is a differentially private algorithm that operates on databases, it guarantees that it hides every single one of the data points in its database. Because no matter how this data point would have changed, the outcome distribution would have remained roughly the same. That's the only takeaway I need from this slide. Make sense? Okay. So the idea in the generic construction that uses differential privacy in order to construct robust streaming algorithms is to use differential privacy in order to protect not the data items in the stream, but instead to protect the internal randomness of your streaming algorithm. So typically differential privacy is applied in order to protect data, but here we don't want to protect data. The adversary chooses the update in the stream. We cannot hope to hide the updates in the stream from the adversary. What we want to hide from the adversary is our internal randomness. So intuitively, if we manage to design a streaming algorithm that guarantees differential privacy for its internal randomness, then intuitively the adversary throughout the execution learns basically nothing about our internal randomness. And then intuitively we are kind of back in the oblivious setting where the adversary knows nothing about our randomness. So that's like a very high level overview of the idea. And here is kind of a more formal formulation of this transformation. So I start with a classical non-robust streaming algorithm A, and I want to design a robust streaming algorithm B that uses A. So for algorithm B, it's just in my head. I'm thinking about its input as a collection of P random strings, where P is a parameter. It'll depend on the specific problem that you're trying to solve. Okay, so I take P random strings as an input, and I instantiate P copies of the classical algorithm A, each copy with its own random string as its internal randomness. Now, every time I get an update in the stream, I feed it to all of the copies of algorithm A. And on query time, when I need to return an estimation for the function that I'm computing, I query all of the copies of A. This gives me like P intermediate outputs, Y1 till YP. I take these intermediate outputs and run a differentially private algorithm on these intermediate outputs in order to come up with a differentially private value that's hopefully good with respect to the problem that I'm trying to solve. Okay, so these intermediate outputs, that's like the database of the differentially private algorithm that I'm running on every step. And hopefully, for the problem that you're thinking about, you would be able to construct a differentially private algorithm such that if, let's say, most of these intermediate outputs are good, then also the outcome of your differentially private algorithm is also good for the problem at hand. So that's the general overview of the construction. And the first, when you want to analyze this, the idea of the analysis of this algorithm B is, first we need to understand that algorithm B is differentially private with respect to the collection of random strings that it gets as input. And why is that? We said differential privacy requires us to hide every single one of our input points. So let's see what happens when only R1 changes. If only R1 changes, that affects only the first execution of the oblivious algorithm A, which means that on every time we query, it affects only Y1 and does not affect all of the other Ys. So it only changes one item in the database that I'm aggregating with differential privacy. And since I'm using a differentially private algorithm to aggregate that, a change limited only to Y1 is hidden. Make sense? Okay.
So here, so here is differentially with respect is differentially private with respect to the collection of input strings. So here you basically don't think that those strings are random. It's for all these strings, right? Sort of.
So when in reality, when I run algorithm B, then it doesn't take as input random strings. It just samples them uniformly. But for the analysis, I want to say that this algorithm, if it were to get these strings as input, then it would be differentially private with respect to any single one of them.
Yeah. So I'm saying this randomness for the input string is not for the privacy, but because of A is randomized. A is randomized, and these are
A is random.
Yes, exactly. These are the C's for that. Yeah, sort of.
Exactly.
Okay, great.
Okay, so so we understand that this algorithm is differentially private with respect to this internal randomnesses that we run algorithm A, and very like waving hands. This means that the adversary that interacts with algorithm B learns very little information about the internal randomnesses with which we instantiate algorithm A, and as a result, you could formalize this argument and show that throughout all of the execution, all or the vast majorities of the copies of algorithm A, they maintain utility, even in the adaptive set. And therefore, if your private aggregation has this property that when most of these intermediate outputs are good, then the aggregated result is also good, then algorithm B would maintain utility. So that's the general overview. This is from a previous result. It's not the work that I'm presenting now. Any questions? Okay, so we get to see this. We understand intuitively why this is a good construction, and now we need to understand what is the space required. So we have P copies of the classical algorithm A. So naturally, our space is going to be something like P times the space of A. And the natural question is, what is P? And what is P? That depends on the specific problem you are trying to solve, because for different problems, you could come up with more or less efficient differentially private aggregation algorithm. Okay, so the question is, what is P? Translates to the question of what is the problem. And that brings me to the problem that I'm trying to solve today, which is the L2 heavy hitters problem. Okay, so in that problem, every single input update in the stream is a standard basis vector, let's say of dimension n, and a real weight. Okay, and so let's say that we got already T such input updates. Then after T input updates, we denote the current, we call it the frequency vector of the stream, as simply the sum of all of the weighted input vectors we got so far. So at time T, that's the current frequency vector defined by the stream. And remember, we are in the insertion deletion model, which here means that these delta i's can be both positive or negative. Okay, so what do we want to compute on every query? So at query time, our goal is to return a set of order of k coordinates, we call them keys, that include all of the heavy keys in the frequency vector of the current frequency vector of the input stream. Specifically, a key I or a coordinate I is an L2 heavy hitter of the current frequency. That should be here ft. A key I is an L2 heavy hitter of the current frequency vector of the stream if its value in absolute value, if its magnitude in absolute value is at least 1 over root k times the L2 norm of the current frequency vector. Okay, so your goal is to output a set of at most O of k coordinates that contains all of the keys for which this holds. If your set contains all of these keys, then your output is correct. Otherwise, it's not correct. Make sense?
So potentially one can output more than k coordinates.
Yes, you could output like 10k, that's fine.
I see, as long as it contains the heavy hitters.
Yes.
Great.
And in the non-adaptive setting, there is a classical algorithm for solving this problem. It's called CountSketch. I'll remind you what it is in a minute. That uses space roughly K. Okay. So we understand the problem. We now can think, what would I get for that problem from the generic construction using differential privacy that I mentioned in the previous slide? Okay, and to that, I kind of need to tell you about a very informal thumb rule for differential privacy, saying that if you want to give out Y outputs with differential privacy, then a very informal statement is that to do that, you need to take at least root Y inputs as your database. So you need to operate on a database of size at least root Y in order to give out Y aggregations with differential privacy. That follows from known composition theorems for differential privacy. Of course, it depends on the specific aggregation or computation that you want to make. It's not for all computation, but it's a general thumb rule. And for the aggregations that we are interested in, that's true. Okay, so we understand this thumb rule. And in our case, we have T query rounds. And during every query round, we need to spit out O of K items as the potential heavy hitters. So overall, throughout the execution, we have a total of T times K outputs that we need to compute with differential privacy. So by this red informal thumb rule, this means that the database on which the differentially private aggregation algorithm works on needs to be of size at least root K times root T. That's P. Let's go back for a second to the previous slide. That's the size of the database on which the private aggregation algorithm operates on. So we need that this size, this P, to be at least root T times root K. Okay, and that means that the total space that we will be needing is root T times root K times the space of A, which is K on itself. So overall, the generic construction, when applied to the L2 heavy hitters problem, would give us space that looks like that. Root T times K to the 1.5. Again, it's P times the space of A. Make sense? I'm ignoring logarithmic factors here. Okay, so now I can finally state the result that we get in this work that I'm presenting. First, we show that the classical algorithm CountSketch as is non-robust by our definition of non-robustness, meaning that it cannot support more than a linear number of queries in its size. Second, we show that like semi-mild tweaks to CountSketch cause it to be robust for a quadratic number of queries. And specifically, the space that we get is root T times K, which is an improvement of factor root K over what you get by applying the generic construction to the L2 heavy hitters problem. So that's our gain, the root K from here to here, and the negative result. Makes sense?
Hello, I have a question.
Yes.
Yeah. So does your improvement and the original one can capture the same number of queries?
Yes, the same number of queries. So T is the number of queries. So using the generic construction, in order to support T queries, you need that many space. Root T over root T times K to the 1.5. And here, in order to support T queries, you need that much space.
Okay, thank you.
So so you write K to the 1.5 in the end, then in the middle you write K. So what's the difference here? Or you have an improvement, you are saying?
You mean here versus here?
Yes, right.
Yes. So I'm saying that's like kind of already known.
I see. I already know it. I see. Okay, great.
Yeah, and that's the improvement.
Thanks.
More questions? Okay. So so I stated our results. They are all about CountSketch. So before I show you how can we improve CountSketch or how can we attack CountSketch, I first need to remind you what CountSketch is, right? So CountSketch, it's parameterized. So like we said, it's a streaming algorithm designed for the oblivious classical setting that in particular solves the L2 heavy hitters problem. And it's parameterized using these three parameters. So first, n, like we said, is the dimension of the input vectors. So every input update is a coordinate I between 1 and n, plus a real valued weight. And then the sketch has two parameters. One, we call it d, it's just the size of the sketch. And another parameter b, which is typically of the same order as k, the number of heavy hitters you're trying to identify. We call it the width of the sketch. Okay, so these are our parameters. And before we do anything, before we take any input update, we start by initializing L, which is d over b, pairs of hash functions. So maybe here is an illustration. We think about the sketch as maintaining a matrix with b columns and with L rows, where L is d over b. Okay, so for every row, we have a pair of hash functions. So that pair of hash functions is for that row. That pair of hash functions is for the last row. And in every pair of hash functions, the first hash function maps keys to cells in that row. And the second hash function just maps them to either plus or minus 1. And we think about every cell in this matrix as a bucket. So initially, all of the buckets are initialized as empty. And now, when you get an update, let's say you get an update, the coordinate I and the weight delta, you apply your hash functions on all of them onto I. Let's look at, for example, on the first row. The first row I applied its first hash function onto I got 5, so 1, 2, 3, 4, 5. That says that the bucket in this row that corresponds to key I is this bucket. I go to this bucket and I add to the value in this bucket delta with either plus sign or minus sign, depending on what the second hash function told me. So here, the second hash function is plus 1. I go here, add plus delta. In the second row, I hash the item, the key I, using this hash function. I get a 2. I go to this bucket, and I subtract delta because here the second hash function says minus 1, and so on. So that's how I maintain the sketch throughout the stream. That's like what's written in the slide till here. Does that make sense? Okay. Now, let's say that I want to use the sketch that I have in my hands, this matrix, in order to estimate the magnitude of some key I. The way I do it, I hash key I using all of my hash functions. So for every row, I get a bucket. I go to the value of that bucket in that row, and I multiply whatever is written here with the sign of the second hash function applied to key I. I do it for all of the rows, take the median values of all of these values that I got. And the claim is that that's going to give you, in the non-adaptive setting, in the classical setting, that's going to give you a very good estimate for the value of key I in the frequency, in the current frequency vector in the strip. So why is that? Let's try to understand it. You see, every time you get an update that corresponds to key I, every time this happens, in the first row, you will go to that bucket. You will go to that bucket and add whatever the current delta is. So if you look at the value of that bucket at the current time in the stream, and multiply the value of that bucket with the sign that corresponds to key I, then that is an unbiased estimator for the value of key I. Why is that? Because since every time we add something to that bucket, we add it with this sign. And now if I look at this value and multiply it by this sign, then the sign of key I cancels out. So if the sign is 1, then 1 times 1 is 1. If the sign is -1, then -1 times -1 is also 1. So by multiplying the content of the bucket with the sign of key I cancel out the sign of key I. But all of the other elements that got mapped to this bucket, they have random signs. So in expectation, their contribution is 0. And intuitively, so that means that every bucket multiplied by the sign of I is an unbiased estimator for the value of key I. And intuitively, if you take the median of enough of these values, then that gives you a good estimator for the value of key I. Does that make sense? And one more thing I want to mention about that is, so okay, we know that the sign of key I multiplied by the content of the bucket is an unbiased estimator for the value of key I in the current frequency vector, but what's the variance? So if you think about it, you have a total of n potential keys. Every key gets mapped into the same bucket as the bucket of key I with probability 1/b. So the total, so the variance encoded by just one additional key is something like 1/b times its value squared. And if you sum over all of the n possible keys, then you would see that the variance of the noise in a single bucket is something like that, which is just 1/b times the squared norm of the current frequency vector. So that's the variance of the noise in every single bucket. So let's go back to the previous slide. It means that when I'm using the content of this bucket multiplied by my sign to estimate my current value, it's an unbiased estimator for my value. And the standard deviation of the noise is roughly 1/√b, where b is k, roughly k, so it's 1/√k times the the L2 norm of the current frequency vector. This means that if the value of the ith coordinate is much larger than that, then it sticks out. If it's much smaller than that, then it's just noise. Make sense? So that's CountSketch. Okay. Any questions?
So there are many versions of CountSketch, and
yes.
So, but here you talk about specific version. So does your result also apply to many other of them, or it's very specific?
Okay, so the for the positive result, we introduced tweaks to a specific version,
sure.
And also the negative result we attack a specific version.
I see.
Yeah.
Mm-hmm. Thanks.
Okay, so there are two more things I want to tell you. We'll see how much we will have time for. I guess that the natural order of things would be to first show you the negative result and then justify why I'm speaking about the positive result. But since I predicted that I might be running out of time, then I kind of want to start with the positive result. Make sense? Okay. Great. So before I show you our positive result or the tweaks that before I tell you the tweaks that we introduced to CountSketch in order to make it robust, let's first start with a warm-up that will not gain us much in terms of the space of our algorithm, but maybe it gives us something like a conceptual improvement. So here is a warm-up. Let's just use CountSketch as is. But now, when I want to estimate the value of a coordinate I, instead of using the actual median like we said before, let's use a differentially private estimation for the median. That's maybe something that's worth trying, because we have very good differentially private algorithms for estimating median. That's something where it's a very basic thing in the literature of differential privacy. We are very good at it. Okay. So that seems like a natural way to go about trying to design a private, a robust version of CountSketch. But if you think about it, and still it doesn't gain you anything essentially in terms of the space requirements, because still throughout the execution, you would need to spit out something like T times K items for the heavy hitters. T queries, K items in every query. So still, in order to guarantee that many outputs with differential privacy, you would need to operate on a data set of size root that, so root T times K. And what's your database? The database size is the number of rows, right? Because let's go back to here. You are trying to run a differentially private algorithm for the median of these things. So the size of the number of elements from which you privately estimate the median of, then this number is L, the height of the sketch, which is D over B. So by our previous thumb rule about the number of points we need in order to privately aggregate them and spit out T times K answers, we would need that L, meaning D over B, be at least roughly root T times K. So this means that D, the size of the sketch, which controls our space, is roughly root T times root K times B, and B is K. So it gives me a size of root T times K to the 1.5. So we didn't gain much with this warm-up in terms of space requirements. But still, it's some kind of a conceptual improvement. At least I think it's some kind of a conceptual improvement. Because if you think about it, in the generic construction, we didn't care what the sketch looks like. We just duplicated completely P times. And here, and we kind of tried to hide with differential privacy the existence of one complete sketch. Here, we are just trying to hide one row in our sketch, not a complete sketch. So, like the generic construction would have many copies of that, and say that from the adversary can't learn basically anything about a single copy completely. We hide a lot, a complete sketch. And now we are just saying we will have a single copy of CountSketch, maybe with more rows, but what we are trying to hide is just the existence of one row. So we are trying to hide less, which is good. Typically with differential privacy, when you're trying to hide less, you are in a better situation. It's easier to hide something small than to hide something large. So that's the conceptual improvement. Make sense? And when you see that conceptual improvement, it immediately kind of, it's immediately tempting to ask, okay, I understand the conceptual improvement. I kind of lowered my privacy bar. I'm trying to hide something smaller, and it seems like an improvement. How low can I go, right? I want to lower the privacy bar even further and hide something even smaller. And indeed, that's the way we get our improvement. Instead of trying to hide with differential privacy the existence of a complete row, we will just use it in order to hide one bucket in the sketch. So we will be using differential privacy in order to hide not a complete row, but just the existence of one bucket. We show that that's still enough in order to get robustness in the adversarial setting. And intuitively, it's much easier to hide just one bucket from the adversary than a complete row. And like there are k buckets in this row, and now I'm just hiding one of them. And that's where we get our root k improvement in the resulting space. So that's basically the idea. We will hide less, maintain utility, and improve space. And now what I want to tell you about are just a few of the two of the challenges that come up when you try to implement this idea. So first, the first challenge that comes up is, I told you that differential privacy guarantees that its outcome hides the existence of every single data point in your database. That's in general not true when there are correlations in the database. Differential privacy says that you cannot learn basically anything about me if I'm like a single point in the database. But if the database contains me, and all my family, then you could potentially learn stuff about me, even without me. Then differential privacy will not guarantee in general to hide you if your data is correlated with many other individuals in the data. Okay, and if you think about CountSketch, there are correlations. Inside a single row in CountSketch, the buckets are not independent, because if item I is mapped to the first bucket, then it is not mapped to the second bucket. So I agree, these correlations seems very weak. Maybe they shouldn't cause any harm really, but it completely breaks our analysis, and we don't know how to cope with these dependencies. Even though they are weak, they break the analysis. So to overcome this challenge, we modify the CountSketch algorithm to what we call bucket CountSketch, which is basically the same as CountSketch after breaking the correlations. So we replace CountSketch with a version in which all of the buckets are independent. So now, for every bucket, you have d buckets. For every bucket, you have like a hash function that with probability 1 minus 1 over b doesn't, so when you fix a key with probability 1 minus 1 over b, this key will not participate in this bucket at all. And with probability 1 minus b, it participates in the bucket with either a plus sign or a minus sign. So it's very similar to CountSketch, except that we broke dependencies. So now, in CountSketch, the number of buckets key I participates in is exactly n. And now, it's like in expectation n. Okay. So it's very similar to CountSketch. It doesn't change much in terms of the performances. But we kind of needed to do it in order to overcome these correlations here.
Yeah, so this makes sense. But then in the last slide, in a high-level idea, you mentioned that you can basically only preserve a single sort of row instead of every of them. So is there any intuition why just preserving the privacy for a single row suffices?
Okay, you mean in the Warmup? Why protecting a single row suffices?
Yeah, right. You said the main improvement is that you can only you can simply only preserve hide one row, right? So why this suffices?
One bucket.
Yeah, bucket. Sorry.
Yeah. Yes. So the intuition is that differential privacy, it kind of guarantees statistical validity in the sense that look at what the algorithm gave out with the randomness after you learn something about them. That should be very similar to what you would have get from this algorithm if you were to instantiate it on a completely independent random tree.
Okay.
So I agree. I'm waving hands, and I didn't plan to get into the details, but the intuition is that, or the way the proof is argued about, execute the entire run or the game between the adversary and the streaming algorithm, and then compare the answers that you get from this execution with the adaptive adversary to an execution in which you would run the streaming algorithm, which provides differential privacy with respect to the internal randomness, on the same sequence of inputs, but with fresh independent randomness. Then differential privacy would guarantee that whatever happens in the actual execution is similar to what would have happened over the imaginary execution with the fresh randomness.
Yeah.
That's the intuition.
Mm-hmm. Sure, yeah, okay. So I guess it's fine, yeah. Thanks.
Okay, and so that's the first challenge. We needed to break the correlations in order to make use of the guarantees of differential privacy. And the second challenge is that if you think about it, now when we work with the individual buckets as our privacy unit, this means that overall we have a data set of size D, because we have D buckets. And the size of the database, what I mean is the number of items in the database that I need to protect a single one of them in terms of privacy. So now I have D items to aggregate instead of just D over B, which is good. But still, if you think about it, every time you try to estimate the value of a single key, you do it via just D over B buckets, because this key is not mapped to all of the buckets. The key that you're trying to estimate the value of just participates in something like D over B buckets. So still you're trying to estimate the value of this bucket from only D over B buckets, just like before. So you are still kind of operating on small data sets when you're trying to estimate values. But the observation is that let's fix a specific query round. And let's say that you have a collection H of heavy keys that you're going to identify. So it's something like K keys. It's true that for every one of them, you're going to estimate its value using something like D over B buckets. But the observation is that on average, these are going to be different buckets. So like if you go back to the picture, when you estimate one key, you're going to do it, let's say, with this bucket, this bucket, this bucket, and this bucket. And when you estimate the weight of another key, it's going to be with this bucket, let's say this bucket, and that bucket. And then another key maybe with this bucket, this bucket, this bucket, and this bucket. So on average, during a single query round, every bucket is going to participate in only all of one of the aggregations that you give out. So intuitively, if you think about the entire execution over t time steps, yeah, you have overall t times k aggregations that you give out, but a single bucket, which is what we're trying to protect, that participates in at most O of t aggregations. So that would mean, very hand waving, that it suffices for me to only have a data set of size roughly root t instead of root t times k. So that's the number of elements I aggregate for every calculation, and now I only need it to be roughly root t. There are several delicate issues that come up when you try to formalize this idea. And in particular, we don't know how to make this observation or idea go through using the median estimator, not even with the private version of the median estimator. And we need to come up with a new or a modified way to estimate the frequencies of keys from CountSketch that will make this idea go through, but I don't have time to go over this delicate issue in the fix. But the bottom line is that we can do it. We can modify and come up with a new estimator using the CountSketch data structure that allows us to kind of pay less in composition and get away with a smaller sketch size. Okay, I don't have much time to talk about the attacks. I'll just mention that, so this is an attack on CountSketch as is. I'll just mention that we implemented the attacks, and in this plot, what do you see is that that's the number of rounds we need in order to cause CountSketch to fail as the function of the number of rows in CountSketch. So there are two lines because it depends on how much you want it to fail. If you want it to miss like an item with, you remember we have to identify every item whose weight is at least that. If I want CountSketch to miss an item with 4 times as much, then that's the line, the number of attack rounds I need. If I want it to be just 1, then that's the line. Okay, I'm out of time, so I won't go over any of the details in the attack. I'll just summarize. We showed that CountSketch as is not robust. You can attack it using a linear number of queries. And what happens for adaptive algorithms for the L2 heavy hitters, the existing generic construction would give you space something like root the number of queries times k to the 1.5. We improve it to something like root t times k. And we also show that this analysis, our analysis for the specific algorithm that we come up is tight because we can also attack it using a quadratic number of queries. And that's it. Any questions?
So I have one question.
Yeah.
So in a standard model, so suppose we only want to characterize the space complexity in terms of updates, the number of updates, rather than the number of adaptive inputs. Is there any lower bounds or upper bounds?
You mean in the non-adaptive setting, in the classical setting?
In adaptive setting, yeah, adaptive setting. I mean, now you are stating your results in terms of the number of queries, T, right?
Yes, the number of queries.
But suppose it's just, I mean, this is the burst or the batch update model, it seems to me. I mean, it just if the batch size is just 1, does it make sense?
So I'm trying to understand the question. Do you ask, like in our upper bound, what's the dependency on M, which is like the total number of input updates that we got throughout the stream?
Yeah.
That's the question? Oh,
Yes.
it's polylogarithmic. So it's hidden kind of by this O tilde. It should be multiplied by some polylog of M.
Okay.
Did I answer the question or not?
But this only applies to one queries or multiple queries? Maybe I didn't understand the model too much.
So you have T queries and a total of M input updates overall, and then your space would be something like root T times K times polylog M.
Oh, so sorry. I think my question is, what if there are many queries? For example, the number of queries is almost linearly in the number of updates. Is there any bad bounds? Rather than
so for that problem, well, if you could do better bounds if you assume that the coordinates that you get in every round, the weights of the updates that you get in every round are bounded. The intuition is that if basically the question is saying, let's say that T equals M. What happens? Of course, then can I bound the total space by root M, but can I do better? That's the question, right?
Yes. Yeah.
So you potentially could do better if you assume that the weights of the updates are small. And then hopefully the heavy hitters would not change by much from one update to another. And then you don't need to change your output drastically from one query to another. So here with the burst, it could be that from one query to another, the set of heavy hitters changes completely. And the values of the keys in the stream changes completely from one query to another. But if you just query after every single input update and the input update is small, then potentially your previous set of heavy hitters is still roughly correct. And you only needed to kind of fix the previous output instead of recomputing a new output from scratch. Make sense?
Yeah. Okay. Yeah, thanks.